Okay, I apologize that my voice sounds so raspy, but I do want to go ahead and get you guys started on the polar coordinates notes. And we actually have kind of covered a lot of the stuff you're going to see in this unit because we just finished the vectors unit. And so if you guys look at this picture right here, you just did this exploration, and the exploration said that the pole was another word for the origin. And so we're used to graphing on things where you have an x and a y axis that look like that. And so when we're locating a point that's way out here, we're used to having an x coordinate and a y coordinate. And so that would tell us how far to the left and how far up we had gone to get there. Well, in the vectors unit, we also practiced finding the length of that side right there. We called it the magnitude of that vector. And x and y we called the components of that vector. So this is going to be very, very similar. When I tell you that you go r units and I give you a direction to travel in, that's a polar coordinate because I've told you what direction to face and how far to walk. And we're going to be practicing going back and forth between that form and the Cartesian form, where we look at the components of that point. How far to the left are you? How far up are you from the origin, which we will now be calling the pole? So all of the formulas are going to be provided for you in the quiz and in the notes and everything like that, but it's all right triangle trig and Pythagorean theorem kinds of things. So it says that if P is a point with polar coordinates r and theta, the rectangular coordinates are given by these two formulas, and all that these two formulas are rearranged right triangle trig. So for example, if I told you to plot the point 6 pi sixth, remember that pi sixth is 30 degrees, so another way of saying this point is 6 units towards 30 degrees, so I would go 6 units out towards 30 degrees, like that. If I'm asking you to come up with the x and the y coordinate where that polar coordinate terminates, I'm asking you to come up with the x and y components, essentially. And that makes a right triangle out of the situation. So if I did my right triangle SOHCAHTOA kind of trig, then the x side that I was looking for would use cosine of 30 degrees is equal to the adjacent side, which is the x value, over the hypotenuse, which is the r value, or the r coordinate. And so what this formula right here does is it simply takes that 6 and multiplies it up to the other side. And so in order to calculate the x coordinate in Cartesian form of this very same point, it's the same point, it's just a different way of measuring the location of that point, is to get the x coordinate, I'm going to do 6 times the cosine of 30 degrees, which is square root of 3 over 2. And the 6 and the 2 would reduce, and so my x coordinate would be 3 square root of 3. And so then this formula right here, the y coordinate, has done the same thing, but when you're solving for the y side, that's the side opposite from the 30-degree angle, so it would have been set up as sine of 30 degrees is equal to the opposite side over the hypotenuse or r value. And so you would have 6 times the sine of 30 degrees is equal to y. And so that's what we're going to do down here is y is equal to 6, and then sine of 30 degrees is just 1/2, and so we would get 3. So, so the Cartesian coordinates that are equivalent to this polar coordinate would be 3 square root of 3 for the x coordinate and 3 for the y coordinate. Okay, so I want you to take a second and I want you to try number 2. And just a heads up, if I haven't given you enough time to work it, I'll give you about 15 more seconds. You can always just pause and take a second and actually work it so that you're not just sitting here listening to dead silence. Okay, so hopefully you paused it and you took a second and you at least tried to draw a picture for number 2, because number 2 does have one thing that is slightly different. And so graphically, if I look at this, negative pi fourths is negative 45 degrees. So that is another way of writing that. It's still in polar form because it's still a distance and an angle, but negative 45 degrees would be down this direction, right there. So then the problem is that this negative R value is telling you that you are not going to travel towards negative 45 degrees. It's saying go away 4 units from negative 45 degrees. So you are actually traveling this direction. Okay? And so you have now gone 4 units out that direction away from the negative 45 degrees. So you're trying to find the coordinates at this point out here. And it's important to always keep track of what quadrant you're in, because you always want to have this backup of checking that you've done the formulas and the trig evaluating correctly. And there's not a lot of trig. I mean, we're talking unit circle values and right triangle trig. So if I use my formulas, the x-coordinate at this point out here would simply be r, which was negative 4, times cosine of the angle, which was negative 45 degrees. And so I have negative 4 times negative 45 degrees was down here in quadrant 4, and cosine was positive. Remember, all students take calculus. So cosine was positive square root of 2 over 2. And so that gives me an x value of negative 2 square root of 2, which makes sense because that x value needs to be negative if this point is to the left of the origin. And then I should get the same type of confirmed answer when I do the formula for my y-coordinate. So y equals negative 4 times the sine of my angle, so negative 45 degrees. So I have negative 4 times. Now sine of 45 is still square root of 2 over 2, but sine is negative in quadrant 4, so negative square root of 2 over 2. And so when I multiply those together, I get positive 2 square root of 2. And so the coordinates in Cartesian form would be negative 2 square root of 2 for the x and positive 2 square root of 2 for the y. And so that confirms that you should be in quadrant 2. You went left, but you went up. Okay? Now when you convert the other direction from rectangular into polar, this is where it gets tricky because you literally have an infinite number of correct answers here. But this right here, this formula right here, it's just the Pythagorean theorem. It's been rearranged. Its original form would have been r squared is equal to x squared plus y squared. But it's been rearranged. And then the angle, this one we had you do in that last unit, the vectors and parametrics unit. When you have a point located out in space and you know the x and the y coordinate of that point and you need the angle, you use tangent because we know the opposite and the adjacent legs or components, whatever you want to call them. Okay, so you always want to graph these points first and find out where they are. So if I convert this rectangular coordinate into a polar, so I'm going to try and write smaller so that I don't cram so much in like I did on the previous slides. So x coordinate's positive 2, y coordinate's negative 2, which puts it right in the middle of this, right out here. So I went to the right 2 and I went down 2, right there. And so if I want to find the length of my hypotenuse, I use my rearranged Pythagorean theorem. So plus or minus the square root of 2 squared plus negative 2 squared, which is plus or minus the square root of 8. Okay, now you can simplify if you want to, but you don't have to. And the plus or minus will come into play just like on the previous two. The negative only indicates what direction you're moving. So we'll have to worry about that in just a sec. We've got to mix and match angles and R values. But in order to do that, we have to find theta first. Now this one is hopefully fairly obvious because this is an isosceles right triangle. It's a 45, 45, 90. But you can always do the y coordinate, which was negative 2, over the x coordinate, and you get a tangent value of -1. And so in the case you have the messy answers or the ones with radicals in them and you need to look them up on your unit circle, you would technically be doing inverse tangent. And so when you do inverse tangent of -1, you get -45 degrees. Okay? And so what I'm going to do, I'm going to start showing you what I mean by an infinite number of correct answers, and then I'll have to erase because I'm going to end up taking space over on problem 2. So this is how you mix and match all of these coordinates. Because what we'll be asking you to do is we'll be asking you to give us one polar coordinate with a positive r and one polar coordinate with a negative r. So I'm going to list a bunch of options. So the answer that we just got for our angle was -45 degrees. But another angle that would put us in exactly the same place would be positive 315 degrees. If I rotated to either of those two angles, then if you imagine turning around and rotating and you're facing this direction, if you're facing this direction, then that means that when you start moving towards the point, you're walking forward. And so what that means is that your R is going to be positive because you are walking towards that angle you rotated to. Same thing goes for 315. If you rotated to 315 degrees, then you are facing into quadrant 4, and that means you will walk forwards to get to that point. But remember from the previous slide, you could have walked backwards to get to this point, just like you did when you walked 4 units away from -45 degrees. So I want to know what angle would you have to be looking at so that if you were facing it, you would be walking backwards but still headed down into quadrant 4. Because I want to know what angles would have a negative square root of 8 for their R value. And so one of the answers, if I turned and I faced this direction right here, then to get to this point down here, I would have to walk backwards away from the angle that I'm facing. Well, that angle is 135 degrees. Or I could have started here and rotated all the way around to face that direction, so I could have gone -225 degrees. But both of these angles right here face into quadrant 2, so to get to my point in quadrant 4, I have to be walking backwards, which is what makes R negative. So now I want you guys to try number 2 for just a second while I erase what I've done. And once again, you can always pause because I am getting ready to just jump into number 2 so that the notes don't get too long. Okay, so then this point right here has a negative x and a negative y, which puts it down here into quadrant 3. So -1, negative square root of 3. Okay, so for the most part, I really just need to use the formulas. I get my numbers, but then I need to know where that point is so that I can mix and match my r's and my thetas. So my formula for r is plus or minus the square root of -1 squared is 1, and negative square root of 3 squared is 3. And so I get plus or minus the square root of 4, which is plus or minus 2. And then my angle, so tangent of theta, is equal to the y-coordinate, which was negative square root of 3, over the x-coordinate, which was -1. So it's positive square root of 3. And that is a unit circle value. Or, remember, you can do inverse tangent of square root of 3. And what you get for theta is you get 60 degrees. Now, that's only if you're looking at your calculator. Inverse tangent of square root of 3 is going to give you an answer in quadrant 1. And so that's actually good practice because we know our point is not in quadrant 1. So we know the other angle that would give us that same size reference angle and have the same 30, 60, 90 ratios on the sides would have been 240 degrees. So that gives us good practice for mixing and matching our coordinates. So I'm going to do the same thing I did on the previous problem. I'm going to list 4 of your infinite number of potential answers. Okay? So I'm going to go ahead and start with the one my calculator would have given me. It would have been 60 degrees. And negative 300 degrees would have faced the same direction. 60 degrees would have faced up this direction, right here. The problem is that my point is down here. So if I'm facing 60 degrees, I need to walk away from it. So I need to be going backwards 2 units. The same thing with negative 300 degrees. If I rotate negative 300 degrees, it takes me all the way around to that point right there. And so I have to walk away from the direction I'm facing to get down into quadrant 3. 240 degrees is one of the angles that would actually rotate me and face me into quadrant 3. And so that means that I would be facing forward as I tried to walk to this point right here. And so I would have a positive R value. And I could have also rotated negative 120 degrees, and that means that I would be walking forward again because both of those angles face the point I am trying to move out to. So transforming an equation uses all the same equations as transforming coordinates. It really is just a matter of meeting your goals. So when we convert from polar into rectangular, our goal is to eliminate the r's and the thetas, and we only want x's and y's in our equation. And there's almost always more than one way to go about doing that. But this one right here, and most of the time it just simply means substitution and maybe a little bit of rearranging or simplifying. So like this, you see there's r right here. And so you guys did this in your exploration. We theoretically know what we're going to end up with already. We know we're going to have a circle with a radius of 3 if you remember the exploration, but you can confirm that by simply substituting that formula for r right there. So you put plus or minus the square root of x squared plus y squared, and it's equal to 3. So all I did was substitute. But in this case, it would help me a little bit if I would simplify just a tiny bit, because I've met my goal. I've gotten rid of r, there was no theta, and now it's just x's and y's, but it doesn't look like the equation to a circle. So what would I do to get rid of the big square root on the left side? Hopefully you're thinking to yourself, or you answered out loud, that you would square both sides. So I'm going to take that side and square it, and take that side and square it, and that gets rid of the plus or minus the square root. And I'm left with this nice, pretty graphing form equation of a circle that is centered at the origin. And we'll get into all those details when we actually get into the different types of equations. Right now, we are just converting back and forth between the different forms of equations. We'll begin identifying them and looking at the characteristics of them here in the next day or so. So then example 2, your goals are a little bit harder. You have, once again, several options available to you. One option would be to take the denominator and multiply it up, and that's the way I'm going to do it, because this is the same thing as r over 1, so it's technically a big proportion. One thing that some people do is they go straight for the substituting first, and you can do that, but watch what's going to happen if you do that. If you go straight for the substituting, then this sine of theta right here would get replaced with y over r. And this cosine of theta right here would get replaced with x over r. And what you have done is you have created a big fraction that has little fractions embedded in the denominator, which makes it messier and it makes it harder. So if you go the other route and you rearrange a little bit first, and you take this denominator and you multiply it up to the left side, then what you would have is this. And you would go ahead and you would distribute r through the parentheses. So you would have r sine of theta plus r cosine of theta is equal to 4. And now you can substitute, because now you have these two formulas that can substitute. R sine of theta is y, and r cosine of theta is x, and there is the standard form of a line. And you don't have to put it in slope-intercept form. You don't have to put it in any particular form. You have gotten rid of r's and thetas. You have this nice, pretty standard form of a line, and you can be done with that problem. And once again, we will identify the characteristics and the types of equations later on in the unit. So I want you to pause it for a second, and I want you to give number 3 a try. Number 4 is different and harder than the others, so just give number 3 a try and pause it for just a split second. Okay, so on number 3, once again, you have a couple of options available to you. You can go straight for the substituting, and you can substitute for r and for cosine. And that's not wrong, but what you can do instead is you could do one substitution step, then rearrange a little bit, and then simplify. And so this is what I'm talking about. If you went a different route, that is perfectly fine, as long as you still end up in the same place. So remember, the formula for cosine of theta was x over r. And so once again, remember that this is r over 1. So technically what I have right now is I have r over 1 is equal to 5x over r. Now this step I never show. I just want to make sure you guys understand that this is technically what I have. But that r value will once again come up and it will multiply up. And so I would have r squared is equal to 5x. Now you can substitute again, or some people can skip the substitution step. We know a formula for r. We know it's plus or minus the square root of x squared plus y squared. But we also know that in this particular equation, r is already being squared. Unlike the previous equation where we had to square it to simplify it, it's already squared, which means that square root will already go away, and we will have this. Now this is still the equation for a circle. Once again, we will get into that later in the unit. It is just a circle that is not centered at the origin, but we have met our goals. We got rid of the r, we got rid of the theta, and we did a little bit of simplifying, and we are perfectly willing to leave it just like that. And then 4 is the strange one of the bunch. It's a completely different can of worms, I guess. You don't have much of an option here. You could substitute for cosine in the denominator. It's really not going to get you anywhere. It's going to make it very messy. So you're going to want to take this and multiply it up to this side. And so you would have r cosine of theta minus 3 is equal to 2. And so then you distribute the r through there again. You get r cosine of theta minus 3r is equal to 2. And all you have to do in this case for the bare minimum is replace r cosine of theta with its formula, that's x, and then replace r with the plus or minus the square root. You have to have parentheses, because if not, it's going to look like it's 3 plus or minus the square root, not 3 times the positive or negative square root. And so this is technically where you could stop. We will talk to you guys in class about the extra credit potential you have for simplifying that and actually converting it into its graphing form. But once again, we have done the bare minimum requirement. We have gotten rid of r and theta. Our equation is all in terms of x's and y's. This is going to end up being an ellipse, for those of you who remember anything about ellipses and that kind of thing. But we're not going to worry about that kind of thing right now. And so then the final conversion is to go in the other direction. So we're going from rectangular into polar. So our goal is to get rid of the x's and y's this time and make sure we're just left with r's and thetas. And we need to, in this case, we need to isolate r or r squared. Okay? So once again, there's lots of different variations of these. So we're going to look at one of each of the more common types. So this right here, you could do a little bit of rearranging, or you can go straight for substituting. We know, once again, I'm going to keep reminding you guys, I know it's repetitive and annoying. We know that this is the formula for r. Well, remember what we've done now twice. We've squared both sides, and so what it gave us was essentially an alternate form. It was straight up the Pythagorean theorem. So x squared plus y squared is automatically going to get replaced with r squared. And you don't have to show a bunch of substitution to do that. You can go straight for the gusto. And then the only thing you would need to do is add the 16 to move it to this side, and then go ahead and take the square root. So r is plus or minus 4. So just like the circle equation that I just did in the previous chunk of problems, we had r was equal to 3, that was a circle. This is a circle. This was the circle x squared plus y squared is equal to 16. So a circle centered at the origin with a radius of 4. And so we've just confirmed that. So then on number 2, we don't have that same option available to us because only one of our variables is squared and the other one is not. And so once again we have a variety of methods and routes and options available to us. I can go ahead and I can move y over first, or I could substitute first. It honestly is not going to matter. I'm going to go ahead and substitute first because that is what people typically do. So x is r cosine of theta, and it's being squared, and y is r sine of theta, and it's not being squared. And so what this first part of the equation becomes is r squared times cosine squared of theta minus r sine of theta. So I've gotten rid of my x's and y's, and I have r's and thetas, but now the trick is I need to try to isolate r or r squared. So because these two terms have two different numbers of r's in them, this one's got 2 r's, it's got r squared, and this one just has 1, I can't just factor it out or anything nice and simple like that. So what I'm going to do is I'm going to move r sine of theta to the other side. And then if I take this and I divide it by r cosine squared of theta and r cosine squared of theta, that'll move that, and it'll get rid of one of the 2 r's over here. So r is now by itself. And then these r's will cancel here, and I will just have sine of theta on top and cosine squared of theta on bottom. And that's definitely the funkiest version of these types of problems. And then the last two are much simpler again. We already know what kind of equation will generate a line from the previous chunk of problems, but this time when I do my substituting in both of these cases, watch what happens. When I replace x with r cosine of theta, and I replace y with r sine of theta, this time both of them have the same number of r's, so I can factor that r out. And inside the parentheses, it's going to leave the cosine of theta plus 3 sine of theta. And it's still all equal to 2. And so the only thing I have to do to get r by itself is take the entire set of parentheses and simply divide it down to the other side. And so this, for those of you who made it far enough through the exploration, you've seen this type of equation before. It's the messiest type of equation. It's an oblique line or an angled line. And I mean, we can look at this. That was the standard form of a line. So we know that's what we're going to be expecting later on in the unit. And then number 4, the final one, actually works out very, very similarly. I think there's only like technically one extra step, actually probably 2. Okay, I'm going to replace the y with r sine of theta, but it's being squared. And I'm going to replace the x with r cosine of theta, but once again it's being squared, and it's all equal to 3. So my first extra step is that I need to actually square both of those parts. And I'm going to erase this to make a little bit of room because I'm running tight on space. So my first term is now 2, because the 2 wasn't squared, just the y was. So then r squared and sine squared. And then 5, and then the r gets squared, and the cosine gets squared, and it's still all equal to 3. Okay, they do have the same number of r's in them, so I factor both r's out of each term. And so I have 2 sine squared of theta plus 5 cosine squared of theta is equal to 3. And then my last step, remember our goal isn't always to get r by itself, we can just get r squared by itself. And so we take the entire messy set of parentheses and divide it down to the denominator. And that is done. Okay, so once again, we're going to work in class. We're going to ask lots of questions. We're going to go ahead and make video notes for the entire unit, whether or not any class is using them as flip notes. That way, as you guys miss classes for AP exams and things like that, or you're absent for other things, you guys can catch up on the whole unit and keep up. If you have any questions, see us for tutoring or ask in class. Thanks.